Welcome to this session on hydrothermal reservoir modeling with CMG. We will build a model for CMG's thermal simulator stars using this grid, which is a reservoir at 2 kilometers depth. We will fill this reservoir porous rock with water and characterize the properties of the rock from a thermal point of view. As naturally occurring, many geothermal systems are naturally fractured, so we'll have a matrix system and a fracture system to characterize. Let's start with the matrix. I'll go to specify property and look for property porosity, which will be 0.15. Then I can scroll over to permeability in the I direction, which is 25. Permeability in the J direction will be the same as I, so I'll go for right click equals I and OK. And then permeability in K direction will be the same, equal times a multiplication factor of 0.1. Now let's also consider the fracture properties. Let's save these properties of the model and let's consider these formulas which are normally used for connecting the intrinsic fracture properties like conductivity and width to the effective fracture properties for simulation models. So you can see here we've got the fracture spacing as the variable in these formulas. We'll need to specify the spacing and then import these formulas in the model. So let's first of all go back to specify property and look for fracture spacing. The size of the blocks in this model is 50 meters. I'm going to assume a fracture spacing of 10 meters in I, J, and 0 meters in K direction, meaning that there are no vertical fractures. Now let's save this spacing on the grid and let's add these formulas under Tools, Formula Manager. Let's define a new formula here called frac perm for permeability. And let's see how to import this formula. This will be independent variable fracture spacing, and it will be equal to 50, which is our assumed value of intrinsic conductivity, 50 millidarcy per meter, divided by the fracture spacing x0. Let's apply this change, save this formula. Let's define a new formula, this time for porosity. That will be frac underscore por. The independent variable will be the fracture spacing, and the formula will be 0.002, which is the assumption on the fracture width, times 2 divided by the fracture spacing, as we saw on the slide. Let's apply this formula as well. And now click OK and go back to the specify property and look for fracture porosity and permeability. So porosity fracture, I go to the specification cell here, right click, formula, and pick fracture porosity. OK and OK. And then let's go to fracture permeability. And we repeat the same process. Formula, frac perm this time. For permeability in the J direction, we are going to assume the same as the I direction permeability. For permeability in K direction, we can input a formula times 2, twice as large. So let's click OK and OK again. We can see also that there is another property already defined in the model, which is the volume modifier. The volume modifier is 1 everywhere on this grid, and it is 100 on the borders of the grid to eliminate any boundary effect. The temperature is not yet defined. We can see that this temperature here is not defined as a property, so let's click specify property and input a temperature of 170 for the matrix and 170 for the fracture as well, assuming thermal equilibrium. Now let's move over to the thermal rock types node. Let's double click on it and define a new thermal rock type. So first of all, we'll define the porosity reference pressure and porosity compressibility, rock compressibility. Apply this change and then go to the thermal properties and we'll specify the rock heat capacity and the thermal conductivity of the rock and the fluid, which in this case is only water. For the calculation of the thermal conductivity mixing, for the overall thermal conductivity mixing, we'll use the complex stars model and apply it. Let's move to the overburden heat loss, which allows us to activate a model that predicts the amount of heat energy lost to the overburden and underburden formations. Let's input data for the volumetric heat capacity of the overburden, and I'm going to assume the same for the underburden, and then the thermal conductivity of the overburden, and I will assume the same for the underburden, and I will apply this change. Let's click OK here to save all this data, and now we move to the components section. We just need to add one component. I'll go to add edit components and add edit a component here. From here I can access a library of components, and I'll pick H2O. Here I can accept star's default data for critical pressure, critical temperature, and the molecular weight. So I'll just click OK. And I could also activate the use ideal gas law on the basis that we are going to be far from the critical conditions of water. I will apply this change and move to the densities tab. In here, I'll input the water density, which is 55500 gmol per cubic meter, the liquid compressibility, which is 7E-7, and the thermal expansion coefficient 8.8E-4. Let's apply this change. And let's go to viscosities now. And here we could either model viscosity of the water phase by using a correlation or viscosity table of temperature versus viscosity at one pressure or multiple pressures. In this case, I've got two tables. The first one is at 15,000 kPa. I'll just go back to Excel and copy the data and paste here. And then with this button, I can add a new table, which will be referenced to a different pressure. I've got 25,000 kPa, and I've copied the relevant data from our Excel file and apply. Let's click OK and move over to the rock fluid section, where I'm going to define some rock types. In here, I need to specify two rock types. So I'll go right arrow button, new rock type, and then again, new rock type. The first one will be used for matrix, the second for fractures. Let's go to the matrix first. And here I've got data from Excel. This will be for water oil table. I don't have capillary pressure data here. will uncheck this box and copy and paste my rel perm curve into Builder and apply. And then I've got my liquid gas table as well, which I'm going to copy paste into here. I will apply this change, and now I'll move over to rock type number 2. Fractures are high permeability conduits, and we're going to assume cross-like relative permeability curves for this. So I'll copy my data for the first table, water oil, so I'll uncheck again capillary pressure, apply, and then I will copy the second table for liquid gas, Ctrl V, and apply. Let's click OK here, and now we'll have to go back to the reservoir section to make sure that the right rel perm curves are associated to the right system. So let's go to specify property and look for property rel perm set number. This will be 1 for matrix, and then I've got rel perm set number fracture, and that will be 2. OK and OK. Now to the initial conditions, the only option here, initialization settings. Here I've got my reference pressure, which is 25,000 kPa, at the reference depth, which is the top of the reservoir at 2,000 meters. The water oil contact and gas oil contact depths will be set to something above the top of the reservoir in order for the reservoir to be fully in the water zone. So let's click OK to save this data and go to the numerical section, which is going to be fully defaulted. As you can see, I'm going to accept the default values, but there is one parameter, which is the DT well, the first time step after any well change, which is not defaulted, and I've got a value of 5e minus 6 for this. And I will just click OK to close this window. Finally, we are in the wells and the recurrent section of the model. Here we can specify our wells. There are various ways of specifying wells in Builder. One way that I could show here is to use the pattern-based wells, which will allow me to define an injector and 4 producers at the same time in an inverted 5-spot configuration. I go for this option, and then I can define, for instance, a polygon within which I want to define my set of wells. In the next section of this wizard, I can specify the injector to producer distance, let's say for instance 500 meters, and pick the type of pattern that I want to have. So the inverted 5-spot, in this case I'll have, as you see, an injector in the middle surrounded by 4 producers. And depending how large the area selected is, I could even fit in other patterns. So that's a matter of maybe optimization or sensitivity studies. But in this case, I'm happy with one being added in here, and I can go and select a well name prefix, for instance, although this is optional. So I can go geoth, for instance, and just go next, next, and then select either the option to perforate all through the model or layers, or select a K layer range from, for instance, 2 to 12. Let's go finish. Now the wells have been defined, and I can scroll down towards the center of the model to actually see these wells, for instance here in aerial view, or I could also quickly go to a cross-sectional view to visualize the injector or maybe the producer wells. Now the wells are not yet complete because we still have to work on the well events, double click on wells and go to well events to set up properties for these wells. So the injected fluid will be water. We need to specify the mole fraction of the injected component and maybe the injection temperature, which will be colder water like 25 Celsius. We can apply this change, but I might not be interested in injected water in this model, so I may consider even shutting in the well and maybe closing the well now and reopen the well later for a sensitivity study on the impact of water injection. So I'll just leave it closed for now. As far as the producers are concerned, I can work on the constraints and change the minimum BHP from 200, which is the default, to 12,000 kPa, and I can apply this change, and also I can add a wellbore model that will calculate the heat and pressure loss from the top perforation up to surface conditions. This is a wellbore model called the semi-analytical model. We can specify the wellbore depth, which will be, for instance, 2000, which is the top of the reservoir. The wellbore length, which is the measured depth, essentially. So by inputting 2000, we are saying the well is perfectly vertical. The well might be cased all the way through, so I could add a casing element here, and maybe there is an insulation string around the tubing, so I could also add an insulation sleeve here by specifying its length. And I can go on and change properties related to the radii, the conductivity of the various elements, the emissivity of each string, and the formation properties, and possibly even the pump location depth and pump power if the pump is needed. I can apply this change and go to constraints wellbore, multiple select them, and copy this information over to the other three producers. By using this right click option, using copy events using filter, I'll select the producer wells, go to dates, first date, and then I go to search and add and click OK, and then OK again. So this completes the well definition. We are now back into at the top into the I/O control, where I could add some output for this model. So there is some default output, but I could also go here and select some special output, which may be very interesting for this geothermal model, because in here, by going to this select button, I could access the well energy output, for instance, which gives me the possibility of selecting a producer well, for instance, and output the energy rate or the cumulative energy produced. By using this insert and copy a row, I can input this output for other wells as needed. And scrolling down here, I've also got pH well output, which allows me to output the temperature or pressure or enthalpy or the steam quality of the produced fluid at three possible conditions: surface, downhole, or pump location, if a pump had been defined. And also there is this output available for OBH loss cum, which is essentially the cumulative amount of energy lost to the surrounding formation. You remember we activated the option to model heat loss to the overburden and underburden. It could be cumulative or via rate. And so I can save this output, click OK to save this as well, and then finally save my model as my hydrothermal.dat, which is now ready to be submitted to STARS for a simulation. Thank you for your attention.